Right, good afternoon, and thanks for having me here. Um, Today's session, anyway, my topic of my session is not about the wonderful marriage of AI and healthcare. I think others have done it so far, and they've done it better than I will do it. Today's session is about issues that are related to deployment and implementing machine learning algorithms in a setting, in a medical setting, in a healthcare setting, for example, medical diagnosis. And those issues, namely two of them, one of them is reliability, and the other one is explainability of machine learning algorithms. So the idea is that, and those two issues can be boiled down to one question. Why should I trust your model? And that's a twofold question. From a physician point of view who uses that machine learning algorithms, the question is that, okay, the algorithm predicts that I have to go to a surgical procedure. So then you have to ask yourself, as a doctor, why the model came out with this solution or with this prediction. What kind of features, or what features were used for that prediction? So you want to be, that has to be a faithful process. And from the patient point of view, why should I trust a doctor who trusts a machine, right? That's more psychology related, and we'll leave it aside. So the idea is and to talk about those two issues. And issues call for action. And we have a toolbox for those issues. The toolbox that we use are AI. So we're going to use AI for AI. So that's the topics of today, and I'll be more than happy to answer questions afterward. So, okay, I'm sorry. So, wasn't me. Just briefly about data science group. Okay, so data science group is based here in Tel Aviv. It's we co-founded data science group with Dr. Gidon Rosenthal. He's here in the audience. About 5 years ago, the idea was to bring and to have an AI expert company that brings a solution to companies here in Israel and abroad in diverse verticals. Other than that, for the last 2 years, we realized that there is a real problem that has to do with what I mentioned before, reliability. So we developed a product called Evolve. And Evolve is a model agnostic solution. It's a SaaS-based solution, which basically try to define drift in your data sets and trying to understand the impact of those drift on your prediction model. And the idea is to do it in an agnostic way, so you don't have to look at internally of the model. So you treat the model as a black box, so you look at the input and output, and then you can be more specific about those changes and how they affect your model. We are about 19 data scientists coming from diverse domains. I don't want to go into it. We've done a lot of work with many domains, but I really want to go to the medical space that we are pretty active in, and we love doing a medical application when it comes to machine learning. So we have like a few projects that we have been doing. We're privileged to do that. One of them has to do with discovery of variant in human genome. This is with a startup located in San Francisco Bay. The other one has to do with early detection of breast cancer using a blood test. We've done some work with EMR, electronic medical record, and clinical data, which is unstructured and structured data, namely with deep learning algorithms. And that's the space we live in. Okay. So black box model. So the idea is that most of the models that we work with are a black box. So you have an input, you have your data set, you have the model. Inside the model there is some elements of pre-processing, all right? And then you have the outputs, the prediction. The idea is that in a clinical setting, what you want to understand is how the model came to conclusion about a specific prediction. And more specifically, let's say if you have a model, you have a neural network on the left-hand side, that you have the data, the feature space, right? And then what you need, basically, you need an explainer. You need to provide the human decision maker, which is the doctor, and show him or her why you have come to conclusion that it's a flu. So arguably what you would like to do, you would like to have the explainer artifact, a visual artifact that will highlight, right, the contribution of each of the feature to that specific prediction. So that's basically what we are wanted to do. So that's regarding explainability and interpretability of models. So interpretability or explainability is defined as the ability to explain how a model predicts an outcome based on the inputs, the feature space, the variables that you have, right? So that's also a stamp for a bigger and more comprehensive notion of FET AI, which stands for fairness, accountability, and transparency. And that's also inspired by the wonderful book of Cathy O'Neill, which is titled Weapons of Math Distraction. Please note the math, M-A-T-H. So for those of you who haven't read it, I strongly recommend to do so. So when you look at the benefit of explainable model, there are many aspects to do that, but I'll really want to go over 3 of them. The first one is debug your model. Okay, so you really want to identify a reason for some errors in your data set. Okay, so you do that for fine-tuning, for getting better accuracy of the model, and you wanted to identify and mitigate bias. And bias are something that are built into our models built into our environment. The other thing is validity. Okay, so you want to know that how the model came to a decision. More specifically in some particular patient or some particular cases. And the fairness and the ethical issue are more related to regulation, like such as the GDPR. I'm not going to go over it, but I just want to mention that. So, so benefit of explainable model, let's go for debug the model. So you want to understand reason for systematic error. Here, what you got a data set. This is a toy example for a classifier that tries to classify between dogs and husky dogs and wolf. So the classifier was trained on a lot of images, right? And then successfully, he was good enough, predicting most of them. But then all of a sudden, he decided that the last picture is a wolf and not a husky dog. So the question is that, well, you might think that it's a great model, right? So only one error, okay? But that's not the case, because you want to understand why the model make that prediction, right? So the idea is to ask yourself why. And when you ask yourself why, basically what it's found out that it was using some unimportant elements of the data. By the way, this is not the one I gave. Can you do me a favor, please? This is not the one that I was using. Can you take the one from the... Disc conquis. Disc conquis. דיסק קונקי איפה? נתתי לחגית את הדיסק קונקי שלי. Okay, never mind. I'll do that. Okay, I'm sorry about that. I'm sorry for the interruption. I was under the impression that I have a new version of that, but that's okay. But what happened is that when we looked at those mistakes, all of a sudden we've tried to classify and see what the kind of the features that the mistake was what. And then all of a sudden we found out that basically the background, the snow that was in that picture was the one that contributed to most to that prediction. Meaning that instead of having a classifier that tried to classify between wolves and dogs, husky, all of a sudden you have a snow detector. And this wasn't your intention to begin with, right? So that's an unimportant feature that was used in your classification. And you want to make sure that you understand that. I think that's, this picture speaks for itself when you do validity, right? So the idea is that would you agree to, as a doctor, would you agree to cut open on a surgeon table just because a model said so, okay? And not fully understand why it's doing so. And a doctor will certainly not operate on a patient simply because the model says so. And you as a patient, you don't want to be operated, right? You want to be cut open on a search table. Okay. When it comes to fairness and GDPR, we all know about GDPR, about the privacy, okay, the Bill of Privacy. So basically, Article 2, you have the right of explanation from the patient, from the user, I would say, point of view. And Article 12 allows user to inquire, so why a particular algorithm came to a decision that is specific for them. So that's, there is a built-in trade-off when we come to machine learning between explainability, accuracy, and explainability. Okay, so the idea is just if you look at the graph, so if we locate or position our deep learning, we all love deep learning algorithms, right? On the top upper side of this graph, you see that they provide a lot of accuracy, but they don't lend themselves to be very explainable. So then you're going to the random forest that Dr. Levine mentioned before, right? We're going to support vector machine, right? Doing some classification problem with support vector. And then at the top, at the bottom, sorry, we see the decision tree, which is our very simple model. They provide a lot of explainability, but they don't tend to give a lot of accuracy. So basically, there is a trend line going that you should follow and you should be aware of. So when you come to linear or quasi-linear models, they are very, they provide a lot of explanation. Just, how much I have? 2 or 3 minutes, okay. So the idea is that you can easily understand the model. Because looking at the decision tree, you look at the decision tree, okay, you can easily, you can conclude, you can come up with a rule, you know, because then the decision boundary that was separating your feature space. But what happened is that, what happened if you want to look at complex model? Let's say like this one, right? This is a model that the feature space, this is only 2 features just for the purpose of some demonstration, but imagine that you have more feature, and this data set and this feature space, the data is not linearly separable. So you cannot come up with any hyperplane that can separate the model. So for that we have the 2 methods, AI for AI. One of them is a LIME algorithm, the shape algorithm that help you to interpret. And basically they will work, maybe I don't have enough time, but basically I just will say that LIME is, the idea is that we have to stand for local interpretable model agnostic explanation. And the idea is that we have to provide explanation to human decision maker, and we treat the original model, which is a complex model, as a black box. We don't want to understand the internal of the model. And then we can learn from the locality of a specific or particular patient. We can learn about distribution. And then we can fit a model, a linear model that is explainable. And based on that, we can see that feature and why it's important for that particular patient. So locality is the key word here. Unfortunately, I don't think I have enough time to go over all that, but I will just say that mathematically speaking, what we're trying to do, this is an optimization problem. There's a 2-component. One is the loss function. The loss function is, and one of them is the complexity. The complexity is the omega of G. Complexity of a model is it's very easy. Let's say we take a decision tree. A complexity parameter can determine the depth of the tree, how many attributes you were using. So you want to use as less as possible attribute, because then the model lends itself to more explainability. So the idea is to go to a loss function. You have your f function with that original function, the complex model, and then you're trying to come up with a G function, which is a linear fit to your neighbor data, which is a pi x. So basically, what you do, you're making permutation of your target data around that point, and you're trying to fit a linear model, and then based on that, you'll come up with the interpretation of the model. That's it, right? I guess. Okay. So thank you very much. If you have any question, I'll be more than happy to take them.